Let's do an example that uses Bernoulli's equation in order to talk about an aerodynamic effect. Let's talk about something called stagnation pressure. So I've already showed you an example of something that I called a stagnation flow, which was a flow of a a fluid flow that approached a solid body and came to a standstill at a point. Any place in a flow where the velocity, like both components of the velocity or all the components of the velocity go to zero, is called a stagnation point. And at the stagnation point, it turns out that flows achieve the maximum pressure that they will anywhere in a flow. And that's actually directly attributable to Bernoulli's equation. So what I'd like to do now is predict the maximum pressure in a flow given, that occurs at a stagnation point, given an initial pressure P infinity and an oncoming velocity V infinity far away from an object. So I'm going to draw an airfoil here, and there's a uniform flow of some fluid, which I'll take to be a gas, flowing towards an airfoil. So if we write out Bernoulli's equation at what I would call point A, that would be P infinity plus half rho V infinity squared plus rho G times whatever the height in the flow is at that location. That's a constant along a streamline. So what I'll do is I will identify a streamline that goes from A to the stagnation point, and along that point, that quantity is conserved. In case it equals P plus half rho V squared plus rho G H wherever at like the point O. Now it turns out that at point O the velocity is exactly zero, and so that term goes away. And so really, let's see what else is in there. So there's the difference, there's this rho G times H term that appears on both sides of the equation. But if we think critically about it, like for a gas, rho G times the difference in height is usually a pretty small number. So if I gather the stagnation pressure, there's the three terms, but one of them I would claim is usually very small. So like, for example, let's suppose I have air and the path of air changes by a vertical distance of 1 meter. That works out to about 11 pascals if you work it out, and that's about the most you'll ever see for an aerodynamic object. Anything that's like 10 meters a second is going to have, or higher, for example, is going to have pressure changes associated with V infinity that's at least 6 times that big, and for other objects it'll be a lot faster than that. So let's assume for a moment that that term drops out. So if rho G times delta Z is a negligible number, like it usually is for gas flows, then the stagnation pressure is just the pressure far away from the object plus half rho V squared. That's the stagnation pressure. Okay, that's very interesting, but what can we learn from that? So, we obtained Bernoulli's equation by setting the density equal to a constant. That was required in order to obtain Bernoulli's equation. But the question I want to address right now, is that a good assumption? When is that a good assumption? Well, we can actually use our estimate for our stagnation pressure to try and estimate how much the density would change if it was just changing a little bit due to that. So we can reach back to our definition of the bulk modulus in order to do this. So the definition of bulk modulus was that negative the fractional change of volume, which is equivalent to the fractional change of density, was equal to delta P divided by the bulk modulus. So in this case, the change in pressure within the flow, it goes from P infinity to the stagnation pressure. So the change in pressure is basically the half rho V squared that we just derived. If we use the bulk modulus, So bulk modulus is kind of interesting because it turns out that the square root of bulk modulus divided by density actually is the speed of sound. I'm not going to prove that here. You'll see it in the later chapter where we'll do the the compressible flow. But the square root of bulk modulus divided by density is the speed of sound. So we can sort of use that, to make some estimates here. So, like in summary, the change in density, as long as it turns out to be a small number, the fractional change in density is half times the v infinity divided by the speed of sound squared. So v divided by the velocity divided by the speed of sound is a number called the Mach number. That's named after a person. So the number that's appearing here is half times Mach number squared. So the important bit is that we're finding out that as long as the Mach number, v over the speed of sound, is much less than 1, then the fractional change in the density is pretty close to 0. And so that would become a good approximation. So is that a good approximation in practice? Well, let's look at some typical numbers. So the speed of sound is 340 meters a second at temperatures close to room temperature. And so let me just jot down a couple of speeds that you might care about. So like approximately a cyclist going downhill might be going something like 10 meters a second. A car traveling on a highway would go something like 30 meters a second. And an airplane, like depending on what the airplane was, so like this is like a Boeing 777 takes off at a speed of around 75 meters a second. And so like the associated Mach numbers are 0.03, 0.09, and 0.22, none of which is a particularly large number. And then you're going to square that number and take it in half. And so the relative changes in density are actually very, very small for those kind of like quantities. So in summary, most of the time, even when you're doing aerodynamics with fairly fast objects, the incompressibility assumption is pretty good, except for really high speeds. So like a commercial aircraft, when it's at its top speed at the highest altitude, will close in on I think Mach numbers of like 0.7 are not unheard of for commercial aircraft, but they're not, I think most of the time for most things that you'll be doing, the incompressible assumption is actually pretty good even for gases.